Hello, multi-level modelers. Welcome back for Module 10, in which we talk about checking assumptions for multi-level models. Very hopefully useful module for making sure that the models that you've run really are telling you what you think they are telling you, which is really important. I have a quick note on the previous module in which we talked about generalized outcomes. In other words, outcomes where we don't assume that the outcome variable sort of fits a normal distribution or a continuous outcome. So a lot of folks asked for a little more specific help on this, and Stata and R can do nearly all of these different types of outcomes. So I have just a little table for you if you're interested. If you're not interested in these outcomes, that's totally fine. But so count outcomes are very useful. So a count outcome is bounded at 0. You can't have a negative count, and it follows what's called a Poisson distribution usually, or a negative binomial distribution. So that would be like a count of the number of times something happened. It can be very useful in measuring administrative data, the number of times a particular citation or report was used, so on and so forth. So that's typically called Poisson regression. And Stata has a package, let me go back, called Poisson, and also a multi-level specific command called ME Poisson. And in R, you can do this in LME4 using the GLMER, Gilmer function, and then specifying link equals log, the Poisson family. If you want to do ordinal logistic regression, the command in Stata is ologit. The multi-level equivalent is me ologit. Notice that pattern, you're just adding me to the front. And R has a package called polar for proportional odds logistic regression that works really well. That is not a multi-level thing, so that would be ideal for a situation where you didn't necessarily have nested data, but it allows you to look at ordinal logistic regression. So that's when you have a series of ordinal outcomes, like partial, full, so on and so forth, like different levels. For unordered categorical groups, so these are sometimes used for voting for different parties or things like that you can't put in order. That's a multinomial logistic regression. In Stata, the command is mlogit. MEGLM is the way you would get that to work in Stata, though it's a bit trickier. And then in Stata, or in R, there's a package called nnet that runs a function called multinom. There are several ways to run a multinomial in R, but that seems to work pretty well. And then if you have time data, so time to event or survival analysis, sometimes this is useful. For example, in education, how long it takes someone to graduate. Survival analysis can be helpful, or stay in school. So the command in Stata for that is streg. The multi-level equivalent is mestreg. And then there's a really nice tutorial. There are actually several packages, including one just called Survival in R that does this, but really nice link to someone who is a biostatistician and does a lot of this kind of work. And on her website, she posted some really cool examples of how to do this in R. So a lot of resources out there for other kinds of outcomes if you're ever interested. All right, so let's talk about assumptions. And they are pesky, right? They're that thing that hangs out there that we have to sort of address if we can. So I have my friend Spock here visiting. We'll get to him in just a minute. But last week we talked about how to use HGLMs or GLMMs, as they're also called, generalized linear mixed models, to model all sorts of things that are not normal, including binary outcomes, and as we just saw, lots of other different possibilities. So this week we're going to pivot just a little bit, and we're going to learn about how to check the assumptions of MLMs. This is not something we've talked about before, because I kind of wanted you to see the scope of all the different things that multi-level modeling is able to do. The only thing we haven't covered are cross-classified models, which we'll cover next week. I thought this is a good chance to kind of think a little bit more about how to check assumptions. And the key there is using what are called residuals. If you had me for 608 or a few other folks, I think Dr. Hutton may have done something similar. You've seen a little bit of this process before. If you remember the Star Trek shape of residuals. If you don't and you've blocked it out, I completely understand. But there is a little bit of sort of reading the tea leaves and assessing assumptions and looking at kind of trusting your gut and judging a plot to see if there might be some issues. It's not too bad, but it is something that takes a little bit of practice. And I think about checking assumptions as an icing on the cake step. I do not think it is necessary. You may hear other opinions, but I do not think it is necessary to check the assumptions for every single model that you run, for a null model, for adding one predictor, adding another predictor. For me, it's most important that the model that I arrive at, the last model I run that I think is the strongest or that answers all my questions, that model needs to meet the assumptions of the method. And so that's the one I would check for that final model. And that's the sort of technique that I'll be demonstrating for you. So hopefully we're going to channel Mr. Spock here and live long and well, hopefully not be nonlinear. Hopefully our residuals look okay. So why look at residuals? So residuals, if you didn't have me for 608, residuals are essentially trash. And that's why I have Oscar here. Oscar the Grouch is our resident Grouch and our resident expert on residuals or garbage, right? So why are these things so darn useful? They are essentially what is left after we fit our model. So they are essentially the difference between the observed value of the outcome, which we know, and the predicted value of the outcome that we obtain from our model. So every observation has both of those. It has an observed and a predicted. And the difference between those two is the residual. Residuals can be positive, residuals can be negative, based on whether or not the model is over or under predicting your outcome. They can be large, they can be small, they can take on lots of different properties, but they're really useful to look at and sort of try to figure out what's going on. Garson outlines a few key purposes that I think are kind of good for thinking about residuals. One thing that we're actually doing is we're making sure that the stuff left after the model is actually garbage, that it is not informative. If we see patterns or other sorts of informative stuff in the data, that means that the residuals may not be garbage after all, and that we may need to specify our model again. They can also be useful for looking for outliers or influential observations. That's certainly the case for a statistic called Cook's distance, which is not entirely a residual, but is something similar. It's more of like a diagnostic. All these are sort of diagnostic statistics. We can look for linearity in our model. We can run specification analyses, so we can see if other things predict our residuals. They shouldn't. That's the spoiler alert on that one. And we can check for independence. So lots of different things you can use residuals for. We're primarily going to assess the normality of residuals and look for outliers in this class, but there also are other things you can do with them. I use the analogy of Cheerios when I think about residuals. There are so many different kinds of Cheerios, if you ever thought about it. So there are regular Cheerios, Honey Nut Cheerios, Apple Cinnamon Cheerios. This one down here, the Ancient Grain Cheerios, kind of amazing. But at the end of the day, right, Cheerios are Cheerios, right? They're a little bit different. The flavors are different. I know some of you are like, oh my gosh, you clearly haven't had Honey Nut Cheerios, but they're just like iterations on the same thing. They're taking the same thing and they're slight deviations. And that's what the different kinds of residuals are. And Garson sort of outlines the many, many different types of residuals. And I would not get bogged down in trying to memorize them because the thing is, you're often going to be tied to software. So certain software, whether it's R, Stata, SAS, SPSS, is only going to be able to produce residuals in a certain way because of the way it was designed and the sort of use cases that were included when the software was being developed. And so flexibility is pretty key. But one big distinction is there are marginal versus conditional residuals. Marginal residuals do not include the added effect of the random component of the model. So essentially, marginal residuals just include the fixed portion. Conditional residuals do include the random portion. There are a lot of reasons it may be better to go with conditional residuals because that random portion can actually be pretty important sometimes. Residuals can be raw. This also means unstandardized. This is not as useful in MLM or honestly in regression in general. I tend to like to standardize residuals. They can be studentized, which means they're fixed to a standard deviation of 1, not necessarily a mean of 0, but a standard deviation of 1. They're deleted, deleted residuals. So that's where the standard deviation is excluding certain observations. So those might be better when you have a lot of outliers. I really like just a very clean standardized residual because they should have a mean of 0 and a standard deviation of 1. If they don't, that means that there might be some issues with normality. So that's the one I tend to prefer. There's also a Pearson residual, and that one is scaled according to the metric of the outcome, and then Pearson deleted. So lots of different residuals. The key here is if you can get a standardized residual, that's great. That's one that almost everybody knows how to work with. If you can get a conditional standardized residual, that's even better. But really, any of these will help you kind of do what you need to do to check the assumptions. So regardless of Cheerio, even though I don't know if I want ancient grain Cheerios, those sound kind of gross maybe. Okay, so just a little overview here. There are tons of residual plots, and if you Google checking assumptions for regression models, you'll see a million different plots, added variable plots, QQ plots, PP plots, all sorts of stuff. So we're just going to focus on a couple that I find to be the most useful. It's not that these are the only ones that you can use, but they are sort of quick and dirty and get what you need out of it. So I really like a good histogram or a density plot of the residuals. It's really nice. It gives you a histogram. Your residuals should follow a normal distribution. And it's simple and it's effective. That's a good way of starting to look at things. I also really like an RVF plot, residuals versus fitted. So this is an XY plot where the Y variable, Y axis are your residual values and the X axis are your predicted values. And what you're looking for is kind of an uninformative cloud. You shouldn't see a lot of trends. You shouldn't see a lot of curving or funneling. And if you do, then that could hint to violations of the homoscedasticity or linearity assumptions. But we'll talk about all that in the demonstration video as well. So just to preview a little bit, these are the two plots that I think are most useful. They're also, you can also have a similar Cook's distance versus fitted plot, which works very well for identifying regression outliers. I will also show you how to use that one in this module as well. So I think that can be a useful thing to use. But yeah, really, I try to keep it fairly simple. Just focus on a couple plots, take what you can and get out. So what do you do if something looks strange, right? The first thing to keep in mind is to keep calm and think about how you can check to see if the violation of assumptions really makes a difference. And that the key to that is performing robustness checks or a sensitivity analysis. It is not the end of the world if your residuals are not perfectly normal or if it looks like you violated assumptions. One really nice option is to rerun your model with what are called robust standard errors. And this can be accomplished using this VCE robust option. In Stata, you just put that at the end of your command. I will show you how to do that. Or in R, you can use the robust LMM package, which implements a robust version of what we've been using so far. So that's a great way to sort of attend to issues of particularly non-normality of residuals. If you have outliers, you might consider dropping those observations and rerunning your model. You can do that with the if command in Stata, or you can filter those observations out in R and then rerun your model. You can also use bootstrapping. We don't talk a lot about bootstrapping in this course. I do cover it in my multivariate statistics course. This is a sample replacement approach, which tends to remove bias from our standard errors. It's a great approach, very easy to implement. That can be another way to sort of deal with violations of assumption. So the best solution is probably to do a couple of these things or all of them. And this is really called a sensitivity analysis. So take your original model, compare it to a model with robust standard errors, compare it to a model with outliers removed, maybe compare it to a model with bootstrapping. And what you're looking for is that the story, the significance, and the direction of your coefficients should not change very much. And if it doesn't, you're all good. The possible violations of the assumptions have not impacted your results, which are the things that we're really interested in to begin with. So that's called a sensitivity analysis or a robustness check. And that's the approach I almost always recommend. And I'll show you how to do that next in Stata and R. So that's all I have for this week. Again, a lot of it is applied here. I'm sort of going to show you how to apply these tools, but that should be at least a brief overview of checking assumptions. Good luck, and we'll talk to you soon.